Hello again. Let's continue with the details of the banker's algorithm. So first of all, we need several different data structures to implement the banker's algorithm. These data structures encode the state of the resource allocation system. We need these data structures where n is the number of threads in the system and m is the number of resource types. So we have n and m. N is the number of processes and m is the number of resource types. Based on that, we need available, which is a vector of length m indicates the number of available resources of each different type. If available j equals k, then k instances of the resource type rj are available. Max is an n times m matrix, defines the maximum demand of each thread. If max j equals k, then thread I or process I may request at most k instances of resource type rj. Allocation is an n times m matrix, defines the number of resources of each type currently allocated to each thread. If allocation j equals k, then thread ti is currently allocated k instances of resource type rj. And the last one is need. Need is an n times m matrix, indicates the remaining resources need of each thread. If need j equals k, then thread ti may need k more instances of resource type rj to complete its tasks. So note that need j equals max j minus allocation j. So these data structures can be differ over time in both size and value, but this is the general explanation of the data structures which we need to implement banker's algorithm in this case. So, okay, we know the data structures. So this is the algorithm. This algorithm can be described with these steps. The first step, let work and finish be vectors of length m and n respectively. And we are going to initialize work equals available. So we are going to assign available to work, and finish I will be false for I equals from 0 to n minus 1, which is the number of our processes. So we are going to store the information of which process is finished, which is not finished yet. On the second step, we are going to find an I such that both finish I is false, that means it's not finished, and B, need I is less than work. So we are going to check the processes which are currently continuing, which are not finished, and we are going to check that if the need of that process is less than my work matrix, which is the available matrix. If I can find a process like that, I can assign actually, I can pretend to assign the resources to that process. So if no such I exists, if I cannot find a process like that, I'm going to move to step 4. On the step 3, work will be work plus allocation. Because on the step 2, I have assigned some resources to a process. After that process is completed, the finish of that process will be true, and my work vector will be work plus allocation I, because the process I is going to release its resources. And at the last step, if finish I is true for all I, then the system is in a safe state. So that means I have find a sequence, I have find a path to stay in the safe state for all my processes. Next, we are going to describe the algorithm for determining whether requests can be safely granted. Let request I be the request vector for thread Ti or process Pi. If request j equals k, then process I or thread Ti wants k instances of resource type rj. When a request for resources is made by thread Ti, these actions are taken. The first one, if request I is less than or equal to need I, go to step 2. Otherwise, raise an error, and since the thread has exceeded its maximum claim. In the second step, if request I is less than or equal to available, go to step 3. Otherwise, Ti must wait since the resources are not available. And the last step, third, have the system pretend to have allocated the requested resources to thread Ti by modifying the state as follows. Available will be equal to available minus request I. Allocation I will be equal to allocation I plus request I. And need I will be equal to need I minus request I. If the resulting resources allocation state is safe, the transaction is completed and thread Ti is allocated its resources. However, if the new state is unsafe, then Ti or Pi must wait and the old resource allocation state is restored. I know it's could be seen a bit complicated, but with this example, it's going to be more clear. Actually, it's a simple algorithm. We can illustrate the details with an example. So to illustrate, to understand the use of the banker's algorithm, consider a system with 5 threads from T0 to T4, or like that, P0 to P4. We have P0, P1, P2, P3, and P4. So we have 5 processes. And assume that we have 3 resource type. A, B, and C are our resource types. Resource type A has 10 instances. Resource type B has 5 instances. And resource type C has 7 instances. So on the initial state, we're assuming that we have 5 processes. We have 3 different resource types, and these resource types are A, B, and C. A has 10 instances, B has 5 instances, and C has 7 instances. Suppose that the following snapshot represents the current state of the system. So at the time t, we are getting a snapshot of the system, and this is the snapshot of the system at time 0. So we have allocation matrix, max matrix, and available vector. So basically that means P0, let's consider the P0. P0 has 0A, 1B, and 0C. So that means we already assigned one instance of B to P0. We are not assigned any instance of A and C to P0. So these are the resources allocated for P0. 0 instance of A, 1 instance of B, and 0 instance of C is allocated for P0. Also, we know that the maximum number of needs of P0. So we know that actually P0 can request maximum 7 instances of A, 5 instances of B, and 3 instances of C. So this is the max matrix, are the maximum number of the potential requests by that processes. Actually, we can describe it like that. P4 needs 4 instances of A, 3 instances of B, and 3 instances of C to complete its task. And this is the allocation matrix. We know that every process has got some instances. So let's assume that, let's consider that A. We assign 2 instances of A to P1, 3 instances of A to P2, and 2 instances of A to P3. So that means we used total 7 instances of A. we already know that we have total 10 instances of A. So that means we have just 3 instances of A available. So actually you can compute the available vector based on the allocation matrix and your total number of resources. And then we are going to find the need matrix for this station. We know the allocation, we know the max. So max minus allocation will give us the need matrix. Because, okay, let's consider that. We know that P0 is going to request 7 instances of A, 5 instances of B, and 3 instances of C. But I already assigned 1 instance of B to P0. So that means the need vector for P0 will be 7, 4, and 3. So we can compute the need matrix for all our processes. And that's it. The content of the matrix need is defined to be max minus allocation. And we know that max and allocation from the snapshot. So in this case, we claim that the system is currently in a safe state. Indeed, the sequence process 1, process 3, process 4, process 2, and process 0 satisfies the safety criteria. Because the algorithm works like that. We have an available matrix 2, 3, and 0. Here, sorry. We have available matrix 3, 3, 2. So we are going to try to find a path. We are going to try to find a sequence to assign that resources, that needed resources to processes. But I have just, here again, I have just 3 instances of A, 3 instances of B, and 2 instances of C. So that means I cannot afford, I cannot give the resources to P0. I don't have enough resources as the needs of P0. But I have enough resources to complete the task of P1. So I can assign that resources, that instances to P1. After the P1 completed, my new available vector will be available plus this one. So I've already some instances. Also, P1 has using here some instances allocated for P1. So my new available matrix will be available plus allocation P1. So based on that, I'm sorry. Based on that, we can find a path from P1, P3, P4, P2, and P0. And we can directly say that if we have a path like that, if we have a sequence like that, this system is satisfy the safety criteria, so I can afford that resources. Here we have another example. Suppose now that process 1 requests 1 additional instance of resource type A and 2 instances of resource type C. So the request will be 1, 0, 2, 1 instance of A, 2 instances of C. To decide whether this request can be immediately granted, we first check that request 1 is less than or equal to available. That is that 102 is less than 332, which is true. So we pretend that this request has been fulfilled, and we arrive at the following new state. This is our new state. We must determine whether this new system state is safe or not. To do so, we execute our safety algorithm and find the sequence T1, T3, T4, T0, and T2 satisfy the safety requirements. So we can immediately grant the request of thread T1 because, okay, this is the request. Based on the request, I'm going to pretend that, okay, I fulfilled that requirement. After that, I'm going to check the safety. If the safety is okay, if I'm still on the safe state, and then I can say, okay, I'm going to give that resources to you. So you should be able to see that when the system is in this state, a request for 330 by process 4 cannot be granted. So assume that for process 4, we have a request 330. It cannot be granted since the resources are not available. We have just 2 instances of A, 3 instances of B, and we don't have any instance of C. So we cannot grant that request. Furthermore, a request for 020 by P0 cannot be granted again. Even though the resources are available, I have enough resources to that. I can assign 2 instances of B to process 0. But if I make that fulfillment, my state will be unsafe. If I check the banker's algorithm, I cannot find a path. I cannot find a, let's say, sequence to satisfy banker's algorithm, to satisfy safe state. For that reason, these requests cannot be granted to. If a system does not employ a deadlock prevention or a deadlock avoidance algorithm, then a deadlock situation may occur, as you know. In this environment, the system may provide an algorithm that examines the state of the system to determine whether a deadlock has occurred, or an algorithm to recover from the deadlock. If all resources have only a single instance, then we can define a deadlock detection algorithm that uses a variant of the resource allocation graph, similar to the previous one. We obtain this graph from the resource allocation graph by removing the resource nodes and collapsing the proper edges. More precisely, an edge from process I to process J in a wait for graph implies that process I is waiting for process J to release a resource that process I needs. An edge from process I to process J exists in a wait for graph if and only if the corresponding resource allocation graph contains 2 edges from process I to RQ and RQ to process J for some resource Q, RQ in this case. As before, a deadlock exists in the system if and only if the wait for graph contains a cycle. To detect deadlocks, the system needs to maintain the wait for graph and periodically invoke an algorithm that searches for a cycle in the graph. An algorithm to detect a cycle in a graph requires O n² operations, where n is the number of vertices in the graph. So this is the complexity of that algorithm. Here is the example. On the left side, we have a resource allocation graph. We are going to remove the resources, and based on that, we are going to get just the threads or processes. So this is called as a wait for graph. So based on that, as you can see, we have a cycle here. We can directly say that T2 is waiting for T4 and T4 is waiting for T1, etc. So based on that, we can detect if there is a deadlock on the state or on the system or not. Similar to deadlock avoidance, the wait for graph scheme is not applicable, it's not suitable to a resource allocation system with multiple instances of a resource type. So we turn now to a deadlock detection algorithm that is suitable to such a system. The algorithm employs several time-varying data structures that are similar to those we used in the banker's algorithm. So we have available, we have allocation, we have request. So these are some vectors and matrices. Available is a vector, length of m indicates the number of available resources of each type. Allocation is a matrix with size of n times m, which defines the number of resources of each type currently allocated to each thread. And request is a matrix again in the size of n times m, which is the current request of each thread. If request I equals k, then thread ti or process pi is requesting k more instances of resource type rj. Let's move on the algorithm. Here's the algorithm. Again, it's very similar to banker's algorithm. On the first step, let work and finish be vectors of length m and n, again, respectively. Initialize work as available for I equals 0 to n minus 1. If allocation I is not 0, then finish I is false. Otherwise, finish I will be true. On the second step, we are going to find an index I such that both finish I equals false or and let's say request I is less than or equal to work. If no such I exists, we are going to go to step 4. And here is the step 3 and 4. Sorry. On the step 3, work will be work plus allocation I and finish I will be true. And then we are going to go to step 2. On step 4, if finish I equals false for some I, 0 is less than I, which I is less than n, then the system is in a deadlock state. Moreover, if finish I is false, then thread I or process I is deadlocked. This algorithm requires an order of m times n square operations to detect whether the system is in a deadlock state or not. Here we have an example of detection algorithm. Again, as I said, it's very similar to banker's algorithm, so we can move on directly. To illustrate this algorithm, we are going to consider a system with 5 threads again, or 5 processes from P0 to P4. I have P0, P1, P2, P3, and P4. Again, I have to need to total number of instances. At the initial condition, I know that I have 7 instances of A, 2 instances of B, and 6 instances of C. And at a snapshot time, let's say T0, I have the allocation matrix, request matrix, and available vector. Available means the available resources on my hand. Allocation gives us how many instances allocated for each thread based on each resources. And here we have the request matrix. So resource type, we already defined that. So this snapshot represents the current state of the system. So based on that, we can claim that the system is not in a deadlock state. And that if we execute our algorithm, we will find that the sequence T0, let's say P0, P2, P3, P1, P4 results in finish I is true for all. So let's check it again. I don't have any available resources, but when I check the request matrix, I'm going to start with P0. P0 is not requesting any resources. So that means I can execute, I can run P0. So the first process I'm going to execute will be P0. After P0 finished, my available matrix will be available plus allocation I. So my new available will be 0, 1, 0. I cannot afford the request of P1, but I can I can give the resources for P2 because basically P2 is not requesting any resources. So I can execute P2 as a second process. After the completion of P2, my available matrix will be available plus allocation I. So my new available vector will be 3, 1, 3. I have now 3 instances of A, 1 instance of B, and 3 instances of C. So based on that, I can afford the request of P3, and then I can afford the request of P4, and that's it. Directly, I can find a sequence as P0, P2, P3, P1, P4. And actually that means I can assign all resources which are requested by the each process. So I can I can execute all processes in that order based on this snapshot. Now suppose that process 2 makes one additional request from an instance of type C. Here, instead of 0, 0, 0, we have 0, 0, 1. So we claim that the system is now deadlocked because at the initial snapshot, I don't have any resources. So I don't have any available resources. But still, I can execute P0. After P0 executed, I'm going to get a new available matrix as vector as 0, 1, 0. I don't have any instance of A. I have one instance of B. I don't have any instance of C. If P2 request one instance of C, I cannot claim that resource. I don't have enough resources for that. So that means I cannot execute P2, I cannot execute P3, I cannot execute P4 because I don't have enough resources for that. I have just 0, 1, 0. Based on that, I can only execute P0. So that means I cannot find a sequence to execute all processes. I cannot let's say, create a condition which finish I is true for all I. So actually that means all processes will be executed. So as you can see from here, we can detect the deadlock. Here we can directly say that, okay, based on these snapshot and based on these requests, there is a deadlock in this system. So when should we actually invoke the detection algorithm? Okay, we have the detection algorithm and we have to invoke them. So the question is that when should we invoke the detection algorithm? Actually, the answer depends on two factors. The first one, how often is a deadlock likely to occur? We can know our own system, so based on that, we have to answer how often we are going to face with a deadlock. And second one, how many threads will be affected by a deadlock when it happens? If deadlocks occur frequently, then the detection algorithm should be invoked frequently too. Resources allocated to deadlock threads will be idle until the deadlock can be broken. In addition, the number of threads involved in the deadlock cycle may grow, so we have to be careful about that. If the detection algorithm is invoked at arbitrary points in time, the resource graph may contain many cycles. In this case, we generally cannot tell which of the many deadlock threads caused the real deadlock. When a detection algorithm determines that a deadlock exists, several alternatives are available. One possibility is to inform the operator that a deadlock has occurred and to let the operator deal with the deadlock manually. Another possibility is to let the system recover from deadlock automatically. There are two options for breaking deadlock. One is simply to abort one or more threads to break the circular wait. The other is to preempt some resources from one or more of the deadlock threads. To eliminate deadlocks by aborting a process or thread, we use one of these two methods. In both methods, the system reclaims all resources allocated to the terminated process. Abort all deadlock process. This method clearly will break the deadlock cycle, but at a great expense. The deadlocked process may have completed for a long time, and the results of the partial computations must be discarded and probably will have to be recomputed later. The next one, abort one process at a time until the deadlock cycle is eliminated. This method occurs considerable overhead, since after each process is aborted, a deadlock detection algorithm must be invoked to determine whether any processes are still deadlocked or not. So many factors may affect which process is chosen, including what the priority of the process is, how long the process has computed, and how much longer the process will compute before completing its designated task. How many and what types of resources the process has used, for example, whether the resources are simple to preempt. How many more resources the process needs in order to complete. How many processes will need to be terminated, and is process interactive or batch? So these are the questions before choosing the process we are going to abort. To eliminate deadlocks using resource preemption, we successfully preempt some resources from processes and give these resources to other processes until the deadlock cycle is broken. If preemption is required to deal with deadlocks, then three issues need to be addressed: selecting a victim, rollback, and starvation. So we have to select a victim to minimize our cost, and we have to create a rollback mechanism to return to some safe state, restart process for that state. And the last one, we have to be careful about starvation. In same processes may always be picked as a victim. Okay, I'm going to select a victim to minimize the cost, but if I choose the same victim always, that means there will be a starvation on that point. And actually, that's it for this chapter. Let's take a break for 5 minutes, and then we are going to continue with the main memory.